Neutron stars are fascinating objects in the vast universe. These stellar remnants are born from the explosive deaths of massive stars, known as supernovae. When a star much larger than our Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to a supernova explosion. The core that remains is a neutron star, an incredibly dense object with unique properties. They are the remnants of massive stars that have exploded as supernovae. This explosion is one of the most powerful events in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. The outer layers of the star are blasted into space, leaving behind a dense core. Imagine a star more massive than our Sun compressed into a sphere the size of a city. This transformation is mind-boggling. The core's gravity is so intense that it crushes protons and electrons together to form neutrons, resulting in a neutron star. These stellar remnants are incredibly dense. In fact, neutron stars are so dense that a single cubic centimeter of their material would weigh about 1 billion tons on Earth. This density is due to the extreme gravitational forces at play, which pack the matter into an incredibly small volume. A teaspoonful of neutron star material would weigh billions of tons on Earth. To put this into perspective, it's like compressing the entire human population into a sugar cube. This unimaginable density is what makes neutron stars so unique and intriguing. Their gravity is also immense, second only to black holes. The gravitational pull of a neutron star is so strong that it can bend light and warp space-time around it. This intense gravity affects everything in its vicinity, including nearby stars and planets. Neutron stars emit powerful beams of radiation, making them detectable as pulsars. These beams are produced by the star's magnetic field, which accelerates charged particles to near light speeds. As the neutron star spins, these beams sweep across space, creating a pulsating effect. These rapidly spinning objects sweep their beams across space like cosmic lighthouses. Pulsars can rotate hundreds of times per second, and their precise, regular pulses make them valuable tools for astronomers studying the cosmos. Neutron stars, with their extreme properties and fascinating behaviors, continue to captivate scientists and stargazers alike. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses, triggering a supernova explosion that can outshine an entire galaxy. What remains is a neutron star, a superdense object composed primarily of neutrons. These subatomic particles are packed tightly together, creating an object of unimaginable density. Neutron stars are not just dense, but also incredibly hot, with surface temperatures reaching millions of degrees. These extreme conditions make them fascinating objects for astronomers to study. The density of a neutron star is mind-boggling. Imagine squeezing the entire mass of our Sun into a sphere with a radius of just a few miles. A single teaspoonful of neutron star material would weigh billions of tons on Earth. That's heavier than Mount Everest. The atoms themselves are crushed, leaving behind a sea of neutrons. This extreme density is a result of the intense gravitational forces that govern neutron stars. The gravitational pull of a neutron star is immense, second only to black holes. If you were to stand on the surface of a neutron star, which is impossible by the way, you would experience a gravitational force billions of times stronger than Earth's. This intense gravity warps the fabric of space-time around the neutron star, creating a deep gravitational well. Even light itself is bent by this extreme gravity. The escape velocity from a neutron star is incredibly high, approaching a significant fraction of the speed of light. Section 5. Twisted magnetic fields. Neutron stars not only possess extreme gravity, but also incredibly powerful magnetic fields. These fields are trillions of times stronger than Earth's magnetic field. The magnetic fields of neutron stars are so strong that they can twist and distort the fabric of space-time itself. They can also accelerate particles to incredibly high energies, creating intense beams of radiation. These beams of radiation are what we observe as pulsars, rapidly spinning neutron stars that emit pulses of radiation with each rotation. Section 6. Approaching the neutron star. As you approach a neutron star, you would begin to experience its immense gravitational pull. The difference in gravity between your head and feet would become increasingly pronounced. This difference in gravitational force, known as tidal force, would stretch your body out in a process called spaghettification. You would be elongated like a strand of spaghetti. The closer you get to the neutron star, the stronger these tidal forces become, ultimately ripping you apart. Section 7. Spaghettification, stretching to the limit. Spaghettification is a gruesome but fascinating consequence of extreme tidal forces. These forces are so powerful that they can stretch objects into long, thin shapes, much like spaghetti. This phenomenon occurs in regions of space where gravitational forces are incredibly intense, such as near neutron stars and black holes. As you fall towards the neutron star, the difference in gravitational pull between your head and feet becomes unbearable. The gravitational force at your feet is significantly weaker than at your head, creating a stretching effect. This difference in force is known as a tidal force, and it increases dramatically as you get closer to the neutron star. Your body would be stretched out like a noodle, with your head experiencing a much stronger gravitational pull than your feet. This stretching effect is so extreme that it can elongate your body to several times its normal length. The process is both fascinating and terrifying as it demonstrates the sheer power of gravitational forces in these extreme environments. This stretching would continue until your body is ripped apart. The tidal forces become so intense that they overcome the molecular bonds holding your body together. This process, known as spaghettification, results in your body being torn into a long, thin stream of matter. Spaghettification is not unique to neutron stars. It can also occur near black holes. In fact, the gravitational forces near a black hole are even more extreme, making the spaghettification process even more dramatic. The event horizon of a black hole marks the point of no return, where the gravitational pull becomes so strong that not even light can escape. It's a testament to the incredible power of gravity in these extreme environments. The study of spaghettification not only helps us understand the limits of physical forces, but also provides insight into the nature of the universe itself. By studying these extreme phenomena, scientists can learn more about the fundamental laws of physics and the behavior of matter under extreme conditions. Section 8. Atomic obliteration. Even before you experience the full effects of spaghettification, the intense gravity of the neutron star would have other devastating effects on your body. The atoms that make up your body would be crushed by the immense pressure, collapsing into a dense soup of subatomic particles. You would essentially be compressed into a tiny fraction of your original size. This process of atomic obliteration is a testament to the extreme conditions that exist near a neutron star. Section 9. A cosmic spectacle from a safe distance. While falling into a neutron star is a fascinating thought experiment, it's important to remember that it's a deadly scenario. Neutron stars are the remnants of massive stars that have exploded in supernovae. They are incredibly dense, with a mass about 1.4 times that of the Sun, but packed into a sphere with a radius of only about 10 kilometers. This means that the gravitational pull on the surface of a neutron star is about 2 billion times stronger than on Earth. If you were to fall into a neutron star, the intense gravitational forces would stretch and compress you in a process known as spaghettification. The extreme gravity, magnetic fields, and radiation would make it impossible to survive. Neutron stars also have incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields can accelerate particles to near the speed of light, creating intense radiation. This radiation would be lethal to any form of life as we know it. Additionally, the surface of a neutron star is incredibly hot, with temperatures reaching up to 1,000,000 degrees Celsius. This combination of extreme gravity, magnetic fields, and radiation makes neutron stars some of the most hostile environments in the universe. However, from a safe distance, neutron stars are incredible objects to study. They provide a unique laboratory for understanding the fundamental laws of physics. By observing neutron stars, astronomers can test theories of gravity, nuclear physics, and quantum mechanics under conditions that cannot be replicated on Earth. Neutron stars also play a crucial role in the life cycle of stars and the evolution of galaxies. They can give us insights into the processes that lead to the formation of black holes and the distribution of heavy elements in the universe. They provide insights into the fundamental laws of physics and the extreme conditions that can exist in our universe. For example, the study of neutron stars has led to the discovery of phenomena such as pulsars. which are rapidly rotating neutron stars that emit beams of radiation. These beams can be detected as regular pulses of radio waves, X-rays, or gamma rays, providing valuable information about the star's rotation and magnetic field. Neutron stars also help us understand the behavior of matter at nuclear densities, which is important for understanding the properties of atomic nuclei and the forces that hold them together. So while we may never experience a close encounter with a neutron star, we can still marvel at their beauty and mystery from afar. The study of neutron stars continues to be a vibrant field of research, with new discoveries being made all the time. As our telescopes and detectors become more advanced, we will continue to uncover the secrets of these fascinating objects. Neutron stars remind us of the incredible diversity and complexity of the universe, and they inspire us to keep exploring and learning about the cosmos.